Hello everyone. Thank you for this opportunity. Start with myself. I'm Thiyagarajan, working as a research scientist in Indian Institute of Technology, Chennai, in a project called Indian Center for Lab-Grown Diamonds. Actually, I have finished. I'm right now talking from the southern part of India, which one you can see from that map. And also to say, I finished my PhD in Bharat Ministry nearby that, and then have some affiliations by carry out and by working as a postdoc and research associate experiences at US and China through China to at US and also at Germany for IFMP and at ZDA. It's a center for the research over there. Of course, it's not a big deal to talk about right now. As of my plan of talk, I would like to talk about my topic saying that I'm going to talk about the high pressure experiments. Which one? It will be some kind of somewhat not exactly to say tedious, but it's very how can I say? It's like a very minute work to work on it to study the effect of pressure on different kind of experiments, on different kind of samples. To say, start with the basics and also to how what we are going to measure and also some of the experiments with the diamond anvils and some of the importance I would like to discuss. These are my slides to say. Of course, we know what is the pressure it is. As of that saying, force by area. So if it is area is less, then so that the pressure will be higher. So our unit we used like in a normal scale we are used it Pascal and Newton per meter square. In the practical scale we are using it the bar and pascals. To say in the high pressure measurements we are using in kilobars or in the GPa, which is equal to 1 kilobar in which equal to 0.1 GPa. So the smaller area, I mean, as of in the nature, we can say the center of the sun, there will be some several hundreds of megabar. At sea level, it will be 1 bar. What we are normally will be there, and also to say the bottom of the deepest ocean is 1 kilobar, and then going down till that bottom of the Earth mantle, it's about 2.5 GPa, and at the center of the Earth, it's 360 GPa to say. In that case, what we are what is the importance of this study is that to say that for property of the materials under or around the bottom of the center of the earth to study that. So this topic of research starts from the geophysics. Exactly. There are the artificially we can create some pressures in different kind of methods to say, for example, uniaxial and shear and hydrostatic. So uniaxial is a could be created by the terms of opposite direction, two opposite forces in a face of a cube or in a particular perpendicular direction. If it is if it is parallel to the faces, it's called as shear press. Whereas in the hydrostatic, to say it has to will be in all direction. It should be compressed compress the any material into the shape, but it's I mean any material into the volume, but the shape will be retained. So, for example, in that case, that there will be a damages could be happen in uniaxial as well as the shear press. So, it's not much interested to study the properties of the material under uniaxial or shear press. Whereas in the case of hydrostaticity, there will be some volume will be reduced. So the property will be definitely will be changed. In that case, the shape will be retained, or there will be some phase transition may happen that we will discuss in some later slides. Um, yeah. Pressure transmission. The pressure transmitting medium will produce the hydrostaticity in the material. So the advantages is that if you use a pressure transmitting medium in form of liquid, that will be the that will provide the hydrostaticity properly, and there is no shear press may happen. That will be uniform pressure distribution over all the sample to compress the shape. It does not affect the accuracy of the data, and also to say there will be some disadvantages there. For example, there is a solidification of the liquid, the pressure medium into the solid. There will be some discontinuous pressure drop may happen, but there will be a quasi-hydrostaticity pressure could be used using the talcum powder, which will be a fine powder, and also the NaCl as a pressure transmitting medium also. So I have come across some of the measurements under high pressure, for example, magnetization, resistivity, and XRD and Raman experiments. For that case, we need some devices to produce or to create the pressure environment for the sample. That's called the pressure devices or cells. Uh, for the magnetization, we are using so far we are using the piston cylinder up to 1 GPa, which can be accelerated 1 GPa, resistivity up to 3 GPa, XRD and Raman up to 30 GPa. For the case of right now, we are going to deal, or we are going to discuss about the XRD and Raman, which will be about which can be used using the DAC. That's called a diamond anvil cell. The important point on the diamond anvil cell is the optical window for providing the laser or reaching the sample with a laser or X-ray or something, or um, any external parameter to reach the sample. So the importance of the optical experiments under high pressure is to understand the materials or behavior of the materials uh, under extreme conditions of the pressure. So it will be leading to structural stability and lattice dynamics. So pressure volume relationship could be obtained, and phase transition could be understood, and also the phase diagram could be prepared. So in different of course, everyone know that different geology, it starts with the geology and physics and material science to understand the properties of the material under high pressure. For example, there will be some any kind of property could be changed. For example, the material from insulator to semiconductor, and then the I mean metal, to say conductor, and then the superconductor. Yes, the same sample could be converted in all the phases of the conducting properties. Again saying to say a material of insulator that could be converted into semiconductor, and then to conductor, and then to superconductor, which could be possible. Uh, so diamond anvil cell, I said that the material, that the device could be used for a high pressure measurements with the window for the laser purposes. For example, the diamond anvil cell we are using, that is a important dimensions, and also important parts of that section of the diamond for the culet, table, pavilion, griddle, and ground. This is the naming we are using for it. In that case, so it's a table and culet. We know that. Some of us will definitely, all of us will know that the table is the bottom face, and also the culet is the top face where the sample will be loaded. So what kind of the diamond could be used? It should be a single crystal without any flaws. Typically, it's from half to 1 carat. Type 1, type 2A. Type 2A is a colorless diamond. And most common cut designs will be the circular shaped table and the culet. That saying that the culet and the table should be in a circular form. Modified brilliant cut, that means the number of faces will be more. And Drucker standard cut, that's optimized pavilion. Optimized pavilion, we can say that there is a height of the pavilion could be changed so that the pressure could be modified. The exact pressure could be modified. And also the Bowler Almet cut, it's a company, they are producing that kind of perfect cut called that shaped circular cut. So what will the culet size, as I just before as we discussed, the culet size, by changing the area of the sample or area, we can exert the higher pressures on the sample on it. So for example, 1000 micron, the pressure could be about 20 GPa we can achieve. In that case, finally, for example, 200 microns of the culet size, we can reach up to 100 GPa. For high pressure experiments, in terms of already that as of the topic discussion, the high pressure experiments on for the XRD as well as for the Raman. Here we can see that the two diamonds will be placed. The culet face will be on bottom of each other. It should not be touch each other because it could crack or damage the diamond. Diamond can diamond only can damage the another diamond. So it should not be touch each other. We are using we can say um, something called spacer, or it's called how can I say? It's a spacer, we can use it. So in that case, we can say the XRD, for the XRD, that will be in the transmission mode or diffracted mode. The focused X-ray will come from the one direction. It will be go out of the second. On the opposite direction in the another phase of that. So diffraction X-ray beam will be analyzed to understand the X-ray pattern of the sample. So we can see there is a 2 points. One is the sample, which is our sample, uh, which should be examined, whereas there is one more red dot, that's called a ruby, that we are using with a small amount of Cr3 plus ions, that is you going to be used as a pressure calibrant. because we are applying some load from the external, and we have to know what is the pressure nearby the sample, what is or pressure on exactly on the sample. So for that case, we are using the Ruby. We will discuss about it. What is the Ruby calibration? And then for the X-ray, I mean high pressure Raman, the same setup could be used. We can say that, but for this case, the focused laser will come from the top and it will be retracted in the same direction, same medium itself. So for the same direction, so backscattering mode could be used for a high pressure Raman. So hope we could understand this, the difference between the high pressure XRD and high pressure Raman modes. So preparation of the sample with the DAC for optical measurements, we are using this kind of cell. If you want, any one of you wants, if any one of you wants, I can. If any of you want, I can show the cell over right now. Even I have it right now here. Okay, I will show it if in the discussion time. That's several parts will be there. In the important part, I would like to discuss this point, final one, the gasket. The gasket is important where the sample will be placed. There is a rhenium gasket could be used. It is a strong, and also the soft one is a stainless steel 301 make, and also the beryllium could be used as a gasket. It's a X-ray transparent also. So for example, in that case, we have to make a sample area. So for this case, we are taking that gasket and pressing with a diamond and making some impression, or it's called an indentation on the gasket, and then we are cutting or we are drilling the hole on it. It should be like a 3/3 size of the sample what we are going to use. And also to say, if we find the if we place a hole on it, we are placing some sample and also a red dot, again to say it's a ruby, to understand or to calibrate the pressure, what is exact pressure on nearby the sample. So we can see that already loaded sample, the middle one is a square piece, is a sample, and finally we can say a small ring and circular place of sample, it's a ruby. So it's a sample with a medium. That is a medium we are using. That, as I will discuss before, the hydrostatic medium will be used. In this case, we are using the silicon oil. So the pressure 10 minutes done, I think 5 minutes more. In the pressure calibration, we are using that. There is a shift of uh, pressure dependent shift of in the fluorescence spectra of the ruby. So the energy level of the chromium ions will be changed with the pressure. That shift emitted the fluorescence wavelength. So this is an equation, pressure calibration equation. By knowing that the position of the R1 line or R2 line, we are placing it, and then we can calibrate the pressure over there. So we can understand what is the pressure nearby using of it. So we are just applying the pressure, and then there is a shift of the energy levels of the ruby. That is a shift in the fluorescence of the ruby. That fluorescence, the position of the fluorescence, that's the wavelength, will give the information on the pressure of the sample. So third, I mean, coming to the important topic, to say again, to say diamond optics called for tailoring purposes of the X-rays. So it's a superior than the silicon in terms of radiation hardness, high transparency, and high thermal conductivity. That will be a low thermal expansion. So that diamond will be best medium or best material to have a high pressure, and also for a X-ray transparency. In that case, there is a lot of there are many beam lines called synchrotron facility is available over all the world. I have used, for example, three. It's a lab X-ray system. Everyone knows it. Everyone knows it. That is the energy of the system is about 8 kVA only. That wavelength is a 1.45. That's a copper K alpha source. In the terms of Petra in Germany, it's Hamburg, and also US and France. They are all using that high energy in terms of 60 kVE, so that the wavelength will be very less. So we can obtain a very fine details of the sample, of course, in which laser can penetrate through the optical window of diamond, reaching there, and then it will be in another medium that will be transmitted to the another medium to analyze that. So in that case, we are using that third generation beamlines in terms of synchrotrons with a high energy to understand the or to obtain the X-ray pattern of the sample at the high energy, high pressures. So high pressure Raman experiment. Coming to the high pressure Raman experiments, as of now, I mean, there will be some lot of experiments will be there. I mean, I mean, instruments will be there, but I have used for these three lasers for my experiments of work, high pressure Raman experiments. In that case, 633 nanometer helium ion laser, it could be used for a good scattering and minimal fluorescence, whereas the 532 is it could be used in a excited Raman vibration in a perfect manner. And also the 582 solid state laser, that also could be used to discriminate the spectral as we want, so that the micro Raman could be micro Raman portions could be understood. So in the case of high pressure medium, in the case of in this case we can use silicon oil as a high pressure medium, whereas in the previous case we can use a helium gas as a high pressure medium. So alternatively taken ruby so in this case or in both of the case, we have to take alternatively the pressure calibrant for the PL and also the Raman spectra of the sample. So once we have to do the PL and then Raman, one PL and Raman for a different kind of pressures. So I would like to say some of my results. I guess time up.